Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, good afternoon. So at Russell's request or suggestion, I researched various proofs of the ergodic theorem and the subadditive ergodic theorem. So these are classical theorems going back almost 100 years in the case of the ergodic theorem and to the 70s for the subadditive ergodic theorem. The original proofs were quite hard. Since then, many shorter and simpler proofs were found. Some of the shortest proofs using the maximal ergodic theorem are not so intuitive. So I want to present proofs that are perhaps more intuitive, following works of Kamai, Weiss, Katznelson, and Keane and Steele. So it'll be product of these. So the ergodic theorem of Birkhoff can be stated in a measure theoretic form or a probabilistic form. In the probabilistic form, we have a stationary ergodic process, so xj. So this process is stationary, meaning that the law of any sequence, say x1, x2, up to xn, is the same as the law of a shift x2, x3, up to x plus 1. And this is true for all n, and it follows from this shift invariance that you can shift by more than one. In other words, if we look at the transformation T that sends just the sequence xj to the sequence xj plus 1, this transformation is measure preserving. And so our measure is a probability measure. And then we'll also assume this assumption can be removed, but in the applications, often the process is ergodic, which means that if you have so we assume that the process is ergodic, which means if we have an invariant event or invariant function, so if f is any function of the process, which is measurable and satisfies, okay, I'll write measurable, and is shift invariant, so f is pointwise equal, not just in distribution, but pointwise equal to its composition with t, then f is constant almost everywhere, almost surely. And this assumption is satisfied in many cases. In particular, this holds in the independent case, but in many more cases. So if the xj are independent, then this invariance certainly implies that it's constant. Okay, so in that setting, the ergodic theorem would just say that if we look at the partial sum, so let me write more generally. So the partial sum of size L starting at k will be the sum of xj plus k when j ranges from 0 to L minus 1. Okay, so we'll be interested in the partial sums from various places. And then we have the normalized partial sum, or the average, AL of k, is 1 over L SL of k. And then the theorem states that an of k for any k, but it's enough to talk about, say, an of 1. This converges to the mean, say, the expectation of x1. Of course, by stationarity, they all have the same mean. This converges almost surely. So that's the Birkhoff ergodic theorem. Later, we'll discuss the subadditive version. Okay, so all right, so any questions on the statement? Okay, so there are really two parts to the statement. One is that this actually converges, and then which is maybe the the harder part, and then identifying that the limit is, as you expect, the mean of x1. Any questions or something unclear?
So ergodic is a property of the distribution of the xj.
It's a property of the distribution of the xj and of the transformation t. Okay, so maybe a word about what this means. You can, instead of invariant functions, you can think just of invariant events. So an event b is invariant if t inverse of b equals b, and it's equivalent to just assume that all invariance events have probability 0 or 1. So that's another form of ergodicity. And okay, and yet another form is that for any two sets of positive measure, if you apply t enough times to one, it will intersect the other at positive measure. So you cannot have kind of two sets of positive measure that don't see each other when you apply t. Okay, so that's about the statement. So I want, as I said, there are several short proofs. I want to give the one that is most intuitive and also generalizes to the subadditive case. So as I said, this proof starts with ideas of Tetsuro Kamai. Then there's who wrote a proof in non-standard analysis. Then this was simplified by Katznelson-Weiss and then by Keane, and it's basically his version that I'll show today. Okay, so first, we want to. So first, I want to say that it's enough. It's enough to consider positive variables. So we may assume all the xj are non-negative, because in general you just separate into the positive and the negative parts and prove it separately. Right? So you just write x as a difference of a positive and a negative part, and work with each one separately and get the result. So once we prove everything here is kind of linear, so once we prove it for the positive part, we prove it for the negative part, we can just subtract and get it. So it's enough to deal with this case.
Yuval,
yes?
Is ANI the same as AN J, right?
No, the limit is the same. But again, AN1 is the limit. AN, right? We're summing. These are partial sums from different locations, right? So.
But there's a shift invariance. So does it.
So the shift invariances of the distributions, right? So x1 is not equal to x2. Just its distribution is the same. Sure. So the distribution, so A1 is definitely not A2, but it has the same distribution. Right. Okay. So yes, of course, and also, it's easy to see that they must have the same limit. So AN, right? So I wrote here AN1, but it applies to ANK for any k. This is a limit, right? As n tends to infinity. Okay. All right, but okay, so look at the lim sup. of the ANs. And okay, so instead I'm going to try and make this proof as intuitive as possible, which means not exactly the same as short as possible. So I want to first consider kind of an easy case, which will then generalize. So, okay, maybe one more definition before that. So we have the limb soup. We fix an alpha, which is less than the limb soup. By the way, this limb soup, we a priori don't know that it's finite at all, even though. So maybe I should have added the assumption. So we have stationary, ergodic, and I want to assume that it's integrable. So assume that the expectation of the variables is finite. So let's add that. Okay, to make this statement meaningful. Okay, so we look at this limb soup, which a priori don't know it's finite. So we know it's in 0, infinity. It might at this stage be infinite, but we'll prove it's finite. Okay. If we were talking about the limb inf, it would be immediate that it's finite from Fatou's lemma, but we're talking about the limb soup, so there's something still to prove. Okay, so fix alpha, which is less than the limb soup, and then let's say L of k, these will be random variables. These are the first time that you that the averages exceed this limb soup. So the first L, so that AL of k exceeds alpha. Okay, alpha is certainly a finite number here. Okay, so by the definition of limb soup, this number is certainly finite, but it might be very large. Okay, we might have to wait for long. So case 1 is when these numbers are uniformly bounded. So this is very special. It happens for some ergodic sequences, like periodic sequences, but it will be a good warm-up for the general case. So suppose that these L of k's are bounded, uniformly bounded by some L. This is just a special atypical case, and we'll see what to do in this case and then generalize from that. So in this case, we just take the partial sum and write it. So basically, the idea is to take the interval from 1 to n and cover it by intervals where the averages exceed alpha. So we know there is some interval here where the average exceeds alpha, and this length of this interval, right? So this is this L of 1. The length of this interval is at most L, and then we find another interval where the partial sum exceeds alpha, and so on. And we know that all these intervals are no longer than L. So we stop the first time we cross n minus L, and this decomposition of this series, let's write it now in more formally. So I want to say that the sum of xj, j from 1 to n, this is going to be bigger than the sum I from 1 to some m of partial sums. So this will be partial sums from some k, from some number. Okay, let's write. These are L of ki at ki. Okay, so, and I'll write some more and then explain. This is going to be bigger than the sum of L of ki times alpha, which will be bigger than n minus L times alpha. And here, where each time we choose ki. So we start with k1 is 1, and ki plus 1 will just be ki plus L of ki. Right, so each time we start at 1, we find an interval where the partial sums are large, then we just go to the next, right? So we find this interval, then we go to the next point, find another good interval, and so on. So all these partial sums are larger than their length times the average, right? Because this is greater than alpha. So we get this inequality, and the length of all these intervals will exceed n minus L, because we just keep going as long as we can, and we just have to stop once we exceed n minus L. It's possible that the next interval will overshoot n, so we stop at that point. We don't take the next interval. Okay. Now, this inequality is, completely obvious after you've seen it, and maybe confusing the first time you see it. So please stop me, because this is so. Apologies for those to whom it's trivial, and apologies to those for whom it's confusing. But anyone from the second group wants to ask something. Because this is really the crux of the whole matter. So
probably should have mentioned that A bar doesn't depend. That it doesn't depend on L. That it's the same soup for A and
that's important. Thank you. So that I should have mentioned that A bar is a constant. So thank you. So that's right. So A bar, this lim sup. Thanks. So maybe at this point I should have mentioned. So A bar is. So note that A bar equals A bar composed with T. It is if, in other words, if we, this is related to Anoop's comment. So if we start the partial sums from 1 or from 2, not only it has the same distribution, but pointwise, the partial sums only differ by the first variable. So when we divide by n and take a limit or a lim sup, it doesn't matter. So pointwise, the lim sup of the sequence starting from the first or the lim sup starting from the second, when we divide by n, clearly easy to see it has the same lim sup. So we have this invariance, which means because we're working in the ergodic case, so A bar is a constant, almost sure. Okay, so thanks, Ofer. I should have commented on that. Yes?
It's not just the first term that it differs, but it actually is the last term that's a little
Right.
bit more.
Yeah, so it's so we want it only to differ in the first term. So maybe I'll say this. So an, so a n of 1, equals a n minus 1 of 2. Or maybe I'll write. Okay, Sn of 1 equals Sn minus 1 of 2 plus x1. Okay, so that's better. So because the last term we don't control well, but okay. So now, right. So now divide. Right. So an of 1 equals n minus 1 over n, an minus 1 of 2 plus x1 over n. And now it's safe to take lim sups. Okay, so.
Sorry, what do you get from this last argument?
This is to formally justify this.
Yeah, okay.
Okay, so what Ofer pointed out is that if we just work with averages of length n, then partial sum of length n from 1 and from 2, they differ by a last element, which kind of varies in time. So we don't control it well. We could, but it's easier just to look at just to use this identity, which compares partial sum of n terms to partial sum of n minus 1 terms. And now once we have it in this form, we really can take the lim sup and see this goes to 0, this factor doesn't matter, and so we indeed derive this identity. Okay, so in this case, we're basically done, at least with the existence of the limit, because, and we can easily finish the rest, because now if you take these two sides, right, you divide by n and take a lim inf, so you get that the so here, so the lim inf of, I'll just write it out, 1 over n sum xj, j equals 1 to n, is going to be, well, we take this divided by n and take a lim inf or limit as n tends to infinity. So this is greater than alpha. Okay, and of course, if we could do this for any alpha less than a bar, then we would get that the lim inf equals the lim sup, and so the limit exists. But of course, this assumption that L is constant is very restrictive. So now I don't want to spell out the details in this case. This case was more just to see the key argument in the cleanest setting. Now we're going to just do that same thing in the general case. So in the general case, we can't assume that these LKs are bounded. But what we can do is, given epsilon small, we can pick a large number L, so that the probability that LK, this probability doesn't depend on K, but the probability that this is bigger than L will be less than epsilon. Okay, again, by stationarity, this probability is the same for any k, so I could have put here just L of 1. Okay? So the point is this L of k is a finite number, so it's a finite random variable, but so I can put an L large, so the probability this variable is bigger than that is less than epsilon. And now we want to modify the process so that, so xk star will be xk in the case when L of k is less than L. So these are somehow well-behaved cases. And in the bad cases, so we're going to look ahead. And if the situation is bad, so we need to wait too long, then we're just going to modify the process and put an alpha here. Okay? This is the modified process xk star. And I want to write it as xk plus zk. Right, so zk is usually 0. Just when we are in this case, zk will be, alpha minus xk. All right, so we define xk this star this way, and now and define this, right. So al star of k are the averages. Averages of the xk star, the x, right? So xj plus k, j from 0 to L minus 1. And L, and then we have L star of k is the first L, so that these averages, al star of k, exceed alpha. And now we're in a good position. These are always at most L.
Did you mean X star?
X star, thank you. Yes, that's the whole point. These are averages of the X stars. And now, because L star of k, in fact, it's L of k if L of k is less than L, and it's 1. Right, so L star k is going, so L star of k, what is it? It's L of k if L of k is less than L, and it's 1 otherwise. Okay, so it's certainly always at most L. So now the previous argument applies, and just partitioning the partial sum I from, so now we're going to take n, which is much, much larger than L intuitively, and we're going to take the sum, so the sum j from 1 to n of xj star is going to be bigger by the same argument from before, because we're in a situation of n minus L times alpha. Okay, so it's convenient that all the variables here are non-negative, so terms that we throw away here at the end, we know they're non-negative. Okay, so it's exactly the same argument from before, now proves us this inequality, which is really the key inequality of this step. Right? Any questions? So it's exactly the argument, because we are in that situation where we only have to sum at most capital L terms to get the average that we want. All right. So now, what we can do with this, several things. So first, let's take expectations on both sides. So we get that n times expectation of x1 star is greater than n minus L alpha. And what can we say about this? Well, look at x1 star. It only differs in this case. So it's at most, so this is n times expectation of x1 plus alpha epsilon. Right? Because the difference is just the expectation of this z1, and that difference is at most alpha, and with probability at most epsilon. Okay, so now we're in a good situation. We can divide by n and take a limit as n tends to infinity, and we'll get that expectation of x1 is greater than 1 minus epsilon times alpha. Okay, moving the epsilon to the other side. And this we could do. Note that here now it's x1. It's not x1 star anymore. So this is true for any epsilon. So yet expectation of x1 is greater than or equal alpha. But this was true for any alpha less than a bar. So we can conclude that expectation of x1 is in fact greater than a bar, which is a kind of powerful inequality here, because a bar was the limb sup. So we conclude that this limb sup is in fact finite and bounded above by the expectation. Okay, so now we're almost done. We just still have to argue that the lim inf of the x's gives us is also a bar. And to this we just go back to this. Yes.
Use the fact that epsilon is small, like epsilon could be half in small.
Yeah, but the point that we used it is, I mean, at the end we use the fact that this is true for any epsilon. Right? Once we had this, right, we got this inequality, and now we say this is true for any positive epsilon. So ex1 is in fact greater than alpha.
Oh,
okay. And then we said this is true for any alpha less than a bar. So in fact, ex1 is bigger than a bar. So now in order to go back, notice that the x star have two pieces, have this x and this z. So let's make sure we can control the z's well. And for this, we're going to use what we've already proved for the process x. We're going to use it for the process z. So, expectation of, so so this fact that we've already proved implies when applied to the process Z, which is after all just another stationary process, a stationary ergodic process, that the expectation of Z1 is going to be bigger than the lim sup 1 over n sum j equals 1 to n of the Zj, almost surely. And right, so the z's are a function of the x process, and so they're also ergodic. So any so if you have any ergodic process and you apply a function of that, then you also get an ergodic process, and you just check that from the definition. Thanks, Russ. So all right, so this is something that should be added. Since the z's are a function and an invariant function of the original process, they're also an ergodic process. So we get this inequality. Now we want to apply that, going back to our key inequality upstairs here. So that inequality tells us that, maybe I'll also write that expectation of Z1 we know is at most alpha epsilon. Okay, now let's write this inequality as in the form 1 over n sum j from 1 to n of xj plus sum j from 1 to n of the zj is at least n minus well over n times alpha. Okay, now we want to take lim inf of both sides. Well, here it just converges to alpha. What can we say about the lim inf of this side? Well, on the one hand, it's bigger. So we take the lim inf. And on the one hand, it's bigger than alpha from that inequality. On the other hand, it's certainly, well, what can we bound it above? It's not true that the lim inf is bounded above by the sum of the lim inf, but it's certainly true that it's bounded above by the lim inf of the x's plus the lim sup of the z's. Right? So this is just true for any two sequences. But when we add them, we can bound right, we can bound above the lim inf by the lim sup of one and the lim inf of the other. Okay, but right, so this is lim inf of an of 1 plus, and this we know, so can be bounded above by alpha epsilon. This is greater than alpha. And so we're in the same situation we wanted before. We move alpha epsilon to the other side. And so we get that this lim inf is in fact greater than alpha. So it follows that this lim inf is in fact greater than a bar. So it's equal to a bar. And we have the convergence. And we've already verified that let's see what Right, so we have convergence to right, so A bar okay, so so here I guess I've explained why A bar is at most the expectation. Why is I didn't say why A bar is at least the expectation. So this is the final note. So this is the fact that it's at most the expectation we've proved. Now in the bounded case, if the x's were bounded, we certainly know that A bar would be equal to EX1 just from the Lebesgue bounded convergence theorem, because all the averages will be bounded by the same bound. And so in general, A bar is bigger than the limit of 1 over n sum j from 1 to n of the minimum of xj with m, which is, right, so this is now a bounded process. So this gives us expectation of x1 minimum m. So A bar is bigger.
Wait, what's in parentheses there?
Xj minimum with a large number m. This wedge is the minimum. Right, so again, in the bounded case, just Lebesgue bounded convergence theorem gives you that the expectation of the limit is the limit of expectations. In the unbounded case, you just truncate, you get this inequality, and now once we have this inequality, you can let m tend to infinity, and you get that A bar will also be greater or equal than Ex1, just by taking m to infinity. Okay, so any questions about this? All right, so as I said, there are other proofs. This one is particularly well adapted to generalization to the subadditive case. Historically, when the Kingman first proved the subadditive ergodic theorem in the 70s, the proof was much harder. So I'll go on to that if there are no questions on this case. Now, despite the name subadditive ergodic theorem, I'm going to prove the superadditive version. So, but it's just up to negate taking minuses. So we're going to so what's a superadditive process? So maybe first just one word on the kind of places where subadditive ergodic theorems get applied. So one place is when you, in first passage percolation, you have, say, a lattice, and you want to, and on the edges, you have random variables which indicate passage times, and you want to find t of 0n is the time to go from 0 to n. In general, t of mn might be the time to go from m to n on the x-axis. So we have 2 points, m and and n on the x-axis, we look at all possible paths that go from one to the other. For each path, we look at the total passage time of the path, and we minimize over all these paths. So on the edges are endowed with independent random variables, which are passage time of these edges. So these random variables, it's easy to see that they're subadditive. So the time to go from 0 to n is certainly bounded by the time to go from 0 to m plus the time to go from m to n. Because here we're considering a larger ensemble of paths that go from 0 to n. Here we're considering paths that, on the right-hand side, we're considering paths that go from 0 to m, but have to go via the intermediate point m. So here we're minimizing over a larger ensemble of paths. So this is the kind of quality. And then you want to show that when you take the time to go from 0 to n, you divide by n. This actually has a limit, and the limit is non-random, so it's almost really constant, and it's equal to the limit of the expectations. So this is one kind of application. Another application is for random walks on groups, and you want to show that the random walk has a speed. So you have some Cayley graph. You're doing a random walk on the Cayley graph, and you look at the distance from your starting point to the nth point in your walk. And again, you can check that that satisfies such an inequality, and so get existence of a limit. So I won't talk now about more applications, but rather go to the formal statement, since I want to finish in time. So the subadditive ergodic theorem of Kingman, and I'm going to state it in superadditive version. So again, we can think of some underlying probability space. So in this case, the probability space is just all the edges on all the random variables that indicate the passage times of the edges. And you can think of a transformation T from omega to itself, which is measure preserving. And then the important things are random variables y, mn. So you can think of these as, say, the negative of these passage times. Okay, and y, mn, they satisfy the subadditive inequality. So I'll just write y0n is I'm sorry, the superadditive. So this is bigger than y0m plus ymn. So that's one assumption. And also the shift invariance in distribution. So ymn composed with t is ym plus 1, n plus 1. So you see, in this situation, the transformation is just shifting the random variables. And you see that the time to go from m plus 1 to n plus 1 has the same law as the time to go from m to n. It just corresponds to the shifted passage times. Okay, so these are the assumptions. And then the conclusion is that if you take what? So, no, this is a little confusing. This is not equality in distribution. This is the actual random variables. Okay, so T is measure preserving. That's right. Okay, so you really think there's really just one sequence of, just like in the ergodic theorem. Yeah. So So here you should, okay, so just think of the basic variables as these ymn, or y0n, and then from y0n you can, and the transformation, you have all the variables. Okay, but the transformation just shifts the underlying space. Okay. So then, right, then the conclusion is that there exists the limit of y0n. This limit exists almost surely. Now beta is some number. It's not, in this case, it's not minus infinity, but it could well be infinity. Okay, the numbers y, these are finite numbers, but I didn't assume integrability here, so certainly averages could go to infinity. Okay, and also beta is also the limit of the expectations. Yes. Thank you. So it's ergodic. Okay, so the proof is, as you'll see, it follows the same lines as before. So we're going to, so first, if you look at the variables y tilde mn, which are ymn, minus the sum yk minus 1 k from m plus 1 to n, then you could just see that the superadditivity assumption implies that this is non-negative. Okay, so leave that as a little verification. You just recursively apply this assumption again and again. And remember that this assumption together with the one on the right implies that we have the superadditivity along any interval. If you take the interval and break it in two pieces, y of the big interval is bigger than y's of the sum of the y's of the pieces, right? And you just keep breaking it up until you get to this y on intervals of length 1. And so this is non-negative. And okay, so and this partial sum can be treated with the ergodic theorem. So okay, if these variables have infinite expectation, then you easily conclude that the limit is infinite. If they have a finite expectation, then you can just use the ergodic theorem that tells you that the averages of these will go to their mean, and you just reduce the case of ymn to the case of y tilde. So because of such a definition, so this allows us to assume that the original ymn are non-negative.
So you are assuming that y has an integral including plus or minus infinity.
Yes. So right. So let's Yes, that's right. Okay, so
So y is integrable or non-negative.
yes. Okay, so let's first simply assume that these y's are finite. Okay. So, thanks. So then, all right, so this allows us to assume that the ymn are non-negative. So now we just continue with non-negative variables and define as before. So so I guess now I'll call it beta, the lim sup of 1 over n y0 n Okay, we fix alpha less than beta. And define, like before, L of k is the first L, so that when we take y from k to k plus L, this is bigger than L alpha. And L star of k. So now L star of k will be L of k if L of k is less than L, and 1 if L of k is bigger than L. Okay, now the same logic that we've used already twice before will allow us to bound from below y0 n okay, by something essentially n minus L times alpha. I'll write it and then explain, minus the sum over all So I didn't tell you how we choose L, but you can already guess. I'll write it down in a moment. So the sum over all k, so that L of k is okay, and here we choose L, as before, we choose L so that the probability of L of k to be bigger than L is less than epsilon. And then so these L star k, we don't really use them. They just kind of remind us of the argument to get this inequality. Okay, to get this inequality, we take as before, we take the interval 0, n, and we look from 0, we look, do we have an interval here where L of k is less than L? If so, we're happy, and then we continue. But maybe here, when we look here, the L of k is bigger than L. Then we just take a singleton, and we go to the next point. Okay? So, but this singleton was a special point where L of k was bigger than L. Then we go to the next point, and so overall we cover the whole interval from from 0 to n minus L by good intervals where L of k is less than L and bad singletons. So when L of k is bigger than L, we just take that singleton and jump to the next. So overall, from the good intervals, we'll get n minus L times their length, but we're going to lose. And here, so we're going to lose from these. So we have this also, the alpha multiplies this as well. So maybe I'll write it this way. sorry, n minus L minus the sum, all of this multiplies alpha. Right, so the total length of the good intervals is at least n minus L minus the sum of the bad locations, the number of the bad locations. Okay, in the bad locations, we had to go to the next point. Okay, this is somehow the key to this proof, but it's similar to the keys to the previous proofs. That's why we went through that.
If you have a bad location, then the next one is not going to be bad as well?
Maybe, but you see, it kind of does give some negative information, but this is not the right note. Here I'm not computing probabilities. This is just a combinatorial pointwise inequality, right? That says we gain alpha times the length of the good intervals, and we lose. But what is the total length of the good intervals? It's at least n minus L minus the number of the bad singletons. Every time we see a bad singleton, we go to the next. Maybe that's another bad singleton. But then it will just enter into this sum. So the total length of the good intervals is at least what's written in the parentheses here. And then from them, we get this times alpha. Okay?
Is it the same as the previous argument, except you did both the cases together? Or is there something different?
Yeah, it's essentially the same. What is different here is that we didn't do actually a modification of the process for this. We just kind of paid the price here. But we're in a better position than before because we already have the ergodic theorem and for the Birkhoff ergodic theorem, and we're about to use it. Okay, so that's why we didn't have to go through the same thing, because now when we divide by n and take and we want to take a lim-inf, you see these indicators are just a sequence of because everything is a function of a stationary process. These indicators, you could check, they're also stationary. So if we divide by n and take a limit, we know they converge to the expectation of this indicator. So, and that expectation is just the probability of this event, which is small. It's less than epsilon. So thus, if we divide by n and take a lim-inf, what do we get? Well, here L is constant, so when we divide by n, we're going to get at least alpha minus alpha times 1 minus the probability of L, say of 1 bigger than 1, which is bigger than, L of 1 bigger than L. So this is bigger than alpha times 1 minus epsilon. Okay, and at this point we use the Birkhoff ergodic theorem for these random variables. Which again, because we're in a stationary situation, these themselves form a stationary sequence, so we can apply the Birkhoff ergodic theorem here. And now we're done. The lim-inf here is greater than alpha, and this was true for any alpha less than beta, so the lim-inf equals the value. So the last comment is, why is the limit the same as the limit of the expectations? So you always have, right? So we already proved, so the limit of y0 n over n exists and equals beta. So then from Fatu, if we take expectation, we get that the expectation of the limit, which is beta, is at most the lim-inf of the expectations. But this is a superadditive numerical sequence, so the limit exists. So the limit exists, and so beta is at most this limit. In the other direction, just observe that if you take y0 and say k times n, you can break this up into n intervals of length k, right? So if you take this and divide by n and take a limit, this will be bigger than the expectation of y0k. Okay, because just from the subadditive inequality, you can, or the superadditive inequality, you can break this up into a sum of n summands each on intervals of length k. And then for these summands, you apply the ordinary ergodic theorem, and to get that when you divide these, this is sum of n summands, when you divide by n, you'll get this limit. This is true for every k, so now let's take this. So here I thought of n as tending to infinity and k is constant. So I can, right, so I have this, and this is true, this is exactly our limit beta, and it's bigger than this for every k. So taking a limit gives us the remaining inequality we need. Okay, since I promised to finish at 5, I won't really discuss more applications now, but let me stop here and wait for any questions. Yes?
So what was the benefit of taking the y's to be non-negative?
So we had some, in this inequality here, right, what did we do? We take the interval 0n, and we broke it into good intervals and bad singletons, right? Now, in the bad singletons, all I said is, well, you know, we don't get the good contribution, but we know we get something at least 0. So that's why I could write this inequality. So this gives us, what is in the parentheses is just the total length of the good intervals. And those all give us alpha times their length. The other things I don't know, but it's non-negative.
Also the last L.
Right? Also the last L, that's right. Yes, because we stopped before the end, and okay, so that's where that gets used. Okay, there are no more.
So you mentioned that the first proof used non-standard analysis?
No, not the first proof. The first proof along this argument. So the Kingman proof was classical. But this is, so this line of proof started with a non-standard analysis proof by Tetsuro Kamei in 1982. And then this was, you know, so Izzy Katznelson and Weiss read that proof, understood it, and understood how to remove the non-standard analysis. But they still, and then this was further simplified a bit by Mike Keane and Mike Steele, who gave these, essentially these arguments for the ergodic, for the Birkhoff case and the subadditive ergodic case. You want to compare to other proofs, you can, so say Duret's probability book has a proof for the subadditive ergodic theorem, slightly more general version, but this one applies to most applications. This is what I proved to you is basically the original Kingman version, and but the proof that Duret gives, which follows Liggett, is really much harder to follow and to remember. So here, I think at least the idea is pretty easy to remember.
So if you kind of use here non-standard analysis, will the proof even simpler or no?
The proof, if you assume various, but you prove a completely different statement. So if you want to verify that that statement is actually equivalent, it's much longer. Yes, Sarah.
So what's the relation of this to maximal theorems?
This is a way to avoid maximal theorems. So there's a very short proof of the Birkhoff ergodic theorem that comes from the maximal ergodic theorem, and this was one of the roots of the original proofs. And initially it was thought, oh, this reduction is so easy, so the maximal ergodic theorem must be hard. But then Garcia came up with a very short proof of the maximal ergodic theorem. So if you combine those there is a very, there is a proof even shorter than the one I presented going via maximal ergodic theory, but that one is more mysterious, I'd say, even to the experts. So.
And that's not of the subadditive. So.
Right. That's not, that one doesn't translate directly to the subadditive. Okay, thanks.